Hello, everyone. So this is Tian from Intel. You can call me Kevin. So it's great we have two adjacent tracks both talking about GPU virtualization. And hopefully that also saves me some time on the background introduction and can deal with a good talk for the lunch time. So GPU is becoming very important recently in many segments, including both the 3D graphics, the media, and also the high-performance computing. And so does virtualization. Virtualization also enters many segments, from server to client, from the mobile to IVI. So combine both together, we can say there are strong motivations for GPU virtualization. As long as you need to run a GPU-accelerated task within a virtual machine, you will require some level of the hardware acceleration capability. So this is a talk we will want to address today. So from our point of view, we think the GPU virtualization need to address the three primary requirements. The first absolutely is the performance. We need to have the direct hardware acceleration to ensure the good performance. The second is the feature. We need to ensure whatever features provided by the physical GPU can be presented to the guest. That means including the 3D, including media, and also including computing. Last, definitely we need to share the GPU among multiple virtual machines. So here is some background about the existing virtualization approaches. Possibly for API forwarding, it's a well-studied technology so far, especially the GPU computing. And basically, the idea is just to forward the high-level API calls from the guest to the hypervisor. So you can render that through the graphic driver in hypervisor to gain the acceleration capability. So definitely, it brings good performance and also the sharing capability. But the biggest problem with this approach is feature, because you require intrusive modification into the guest graphic stack. But for different features, they have different graphic stacks. The 3D have DirectX for media and also for OpenCL. So that would be, will means the feature will be lag behind. So what about direct pass-through? We can dedicate the GPU to one virtual machine. Definitely it brings the best performance with the least hypervisor intervention, and it brings all the features what you can see on the native, but there's no sharing, because you can only dedicate one GPU to one virtual machine. Do we have answer to address all the three requirements? This is what we want to talk today. We call it the gVirt. Our main contribution in the full GPU virtualization plus mediated pass-through. When we say the full GPU virtualization, we present each virtual machine with the full-fledged virtual GPU device model, including the 3D media and the computing capability. So we can run the native graphics driver inside the virtual machine to leverage existing quality and also optimization in the native graphics stack. So when we say mediated pass-through, basically means we want to pass through the performance-critical operations to make sure the GPU can accelerate those critical operations with base performance. But in the meantime, we want to trap and eliminate the privileged operations so we can construct the device model, can also manage the sharing. So with this, we can achieve up to 95% of native performance, and also we can scale up to 7 virtual machines. So this is our answer for GPU virtualization. From this figure, you can see each virtual machine runs a native graphics driver inside the virtual machine. As some privileged operations are delivered through the device model, but the majority of the performance critical operations go directly to the GPU. So achieve a good balance among three requirements. gVirt is an open source implementation. Currently, it's under the GPL and BSD dual license. Our initial implementation is based on Zen. So the previous code name as ZenGT. That's maybe some people already know that. And we will have the KVM support coming soon. Currently, our work is based on the Intel processor graphics. It's an integrated GPU, but the principle and architecture should apply to different GPUs. Also, I think the benefit of our work is we have open source implementation. The Intel integrated GPU has all the hardware internals public, the specification public. So together you can do your future research work on this space. Also, currently this technology is trademarked as the Intel gVirt. It's a short name for the graphics virtualization technology for virtual GPU. So in the following slide, I'd like to talk about some challenges to implement the full GPU virtualization. The first is the virtualization complexity. The second is the sharing efficiency, and the third is how we can ensure secure isolation among the virtual machines. First, let's look at the abstraction of modern GPU. So in general, there is a render engine. This implements the so-called hardware acceleration capability. And there's a display engine, basically just trying to display the pixels on the external monitors. And they can be configured through the I/O registers by the graphics driver. If the GPU wants to access the system memory, there's GPU page tables can map system memory into the graphics memory space. Possibly the primary difference between Intel GPU and the discrete GPU is about how graphics memory is implemented. On discrete GPU, there will be on-chip video memory. But on Intel GPU, all the graphics memory is virtualized. They are fully backed by the system memory. That's why we have a dot box here. So in our case, as I said, we want to pass through the performance critical operation. So what operation is performance critical? From our study, we think the graphics memory access possibly the most performance critical operations. In our measurement, when running a typical 3D workloads, the access could be hundreds of thousands access per second. So there are two major purposes on using the graphics memory. One is frame buffer, containing the pixels, vertices, and also depth buffers. Also, there's command buffer, including a primary ring buffer chained into multiple batch buffer, trying to convey the GPU commands programmed by the graphics driver. So for all the two types of resource, we actually pass through to each virtual machine, allow them to direct access. So on the other hand, for the registers, we have to trap and eliminate. And also for the GPU page tables, we must trap and eliminate. We cannot allow guests to use the guest physical address in the page table to ensure the isolation. So that means based on those trap and elimination, we can provide the full-featured vGPU device model. And also for page tables, we just use the shadow GPU page table. That has been greatly discussed in a previous talk by Suzuki. So I think I don't need to go into the detail of how that's implemented. So another interesting thing is how we can take a look at how the render engine is actually shared. Currently, to ensure we have the direct performance boost, so we actually, once the virtual machine is scheduled, we want the direct execution of the guest command buffer. That means for whatever command buffer submitted by the guest, once it gets the current time quantum, we will need the render engine to read the commands that complete the acceleration immediately. And we currently use time-based sharing. So for example, our time quantum is 16 milliseconds. Every 16 milliseconds, the render engine will start to serve a different command buffer. And previously, there's a good question about the, because currently the GPU is non-preemptible, so possibly some bad virtual machine may issue a non-lasting command buffer to the GPU. In our case, currently we use a conservative approach. We have a timeout, for example, 1 second. If the one GPU command buffer executes to none, we will reset the GPU as in trying to serve the second GPU, second virtual machine. So for display management, basically this is usage specific. In some usage, actually people want the virtual machine shown on the physical monitor. In that case, we have a foreground VM and background VM concept. The VM shown on the monitor called the foreground VM. We will have the display engine to read pixel from the foreground VM's frame buffer directly. Then when we switch the background and the foreground VM, we will have a display engine to read a different frame buffer. So this switch is different from the previous render engine scheduling. This is mostly initiated by the user, the end user himself. So this actually comes to an interesting problem where we want to pass through the graphics memory, because now we actually have simultaneous access from different components. The render engine may have access to the graphics memory. Display engine may have access to graphics memory. and also access to a different VM's graphics memory. In the same time, we also have CPU access to the graphics memory. That means we have to do the graphics memory partition between the graphics. We have to do the graphics memory partition, allocate each virtual machine with a part of the graphics memory, and each virtual machine can only access its allocated resource. And that's basically the concept. Also, the graphics memory resource partition leads to an interest problem, which is very similar to the standard system memory virtualization. This will cause an inconsistent view between the guest and the host. From guest point of view, it's a reduced size starting from 0. But from the host side, it may be starting from non-zero and it's discontinuous. That means from virtualization side, we may need to do the address translation in all the reference in the register and in the commands. That will be very complex. So we introduce a new concept called address space belonging. We will expose the graphics partition knowledge into a graphics driver. So each graphics driver will only use the graphics memory allocated by itself and belong out non-allocated resource when the driver is initialized. So this possibly is the only modification we did to the graphics driver, but that modification is very tiny, just smaller than 100 lines of code in the Linux graphics driver. This can avoid address translation, so greatly simplifies the virtualization implementation. The last part I want to talk about is about the security. Because a virtual machine may map unauthorized graphics memory pages. In that case, we just use a mediated pass-through to make sure every virtual machine can only access its granted resource. A virtual machine may program unauthorized graphics address in the registers or in commands. So use the GPU to bypass the CPU, the mediated pass-through check. So in that case, we audit every registered commands before it's accessed by GPU, by the GPU hardware. The last part is the a virtual machine may harm the GPU with many methods. Is somehow a denial of service attack. So for this attack, we invent some detection logic in the hypervisor and trying to recover that situation. But even with those solutions, it's pure software. So there's one problem from the direct execution. This shows the basic flow. We can see when a guest submits the commands, it's intercepted by the mediator, and the mediator audits the commands and then submit to the GPU. At this point, because we direct execute the guest command buffer, the guest graphics driver may modify command at this stage, and then this modified command can be executed by the GPU. So that exposes a small window for the evil things to happen. We developed the smart shadowing to tackle this problem. Basically, utilizing the specific program model from the run buffer and the batch buffer. Given time limitation, I don't go into the detail, just show you the concept. So for run buffer, because it's very limited, and also just the ring structure, we create the shadow run buffer in the hypervisor, but there's no write partition. Every time when there's a submission, we just copy the commands from the guest buffer to the shadow buffer. And it's okay for guest to modify the guest run buffer, but there's no way for guest to modify the shadow run buffer because it's invisible. In this case, we can make sure all the audit on the run buffer are still valid in the whole execution time. The second idea is the write partition of the batch buffer. Batch buffer contains the majority of the render commands from the guest. So for batch buffer, we don't need to create the shadow because essentially it's not accessed frequently after submission. So once we intercept the submission, we just audit and then enable the write partition on the page. So in this case, if guest trying to modify the submitted commands, they will be captured and rejected, or even can lead to the VM be destroyed. But if the guest trying to access the other location in the same page, we will allow that and eliminate. Okay, this is for the previous technique. I will go through a quick performance evaluation in our case. In this case, we just running the Linux virtual machine, including the 3D benchmarks, Let's Mark, Open, Runner. Those are most are the first-person shooting game, also including some 2D benchmarks. You can see most GPU-intensive workloads, we can achieve at least 80% of native performance The base one can be the 95% of native performance. There do have some bad case. For those cases, we actually studied because those cases are not purely GPU intensive. They are also CPU bounded, very CPU bounded. So when we running those workloads, the mediation cost, the trap emulation cost actually have some impact. But if we look at the Windows virtual machine performance, is much better, including both the 3D Mark and Haven 3D and Password 2D. They are generally 80% of native performance and very close to the VTD performance. Maybe I don't need to go through the. We can first look at the scalability. Here we can scale from one virtual machine to 7 virtual machines running same workloads. You can see the first workloads, they are scalability very good. They converge the performance just stays almost the same. There are 2 cases they actually have a big performance difference when jumping from scale from 1 virtual machine to 3 virtual machines. Those 2 performance are more CPU intensive. So when you're adding more virtual machines with more CPU cores, so it will benefit from the CPU side, not from GPU side. And I will not go through the overhead. This just shows with the graphics resource partition. We did experiments on native. Basically, the performance, there's only very limited performance impact. So that's my talk. We contributed the full GPU virtualization plus mediated pass-through, so we can run the native graphics driver within the virtual machine. We can achieve a good balance for performance, feature, and sharing. And if you have interest to do future research, you can access our public available patches. Okay, Christian, welcome. Yeah, maybe switch to another mic or.
Songmin Yi from Samsung Electronics. Great work. It seems like you changed slightly the graphic driver, right?
Sorry?
Seems like you slightly changed the graphic driver.
Right.
My question is that I'm wondering if there is a way to adapt your solution to the target device whose graphic device driver source code is not available.
Yeah, actually, it's a balance between the complexity and the the driver modification. Actually, initially we do have the implementation without driver modification, which are trying to do address translation. But finally, we thought that's very complex and also maybe performance impact. Because we are from Intel, so it's very easy for Linux graphics driver. It's very easy to change. Also for Windows graphics driver, we talked to our driver team because the driver change very small. It's already included in the native graphics driver, so that's not a problem.
Okay.
Yeah.
Hi, this is Long Wen from IBM Research. Okay. So my question is that we know the NVIDIA GPU does not allow preemption. So I want to know if Intel's GPU allows that.
Yeah, I think it's the same case. If you have some non-executing, for example, OpenCL workloads on the submitted, there also, I think, there's a hardware limitation. It's not preempted.
But I think what you said actually the GPU memory is in the system memory, not in the GPU memory, right? In Intel.
Right.
So I think then you can use an in-page fault or such mechanism to interrupt that. Can you?
If you want to preempt the GPU, the more important thing not about memory, it's about the internal state within the GPU, right? If the GPU itself doesn't, support the internal state safe restore, then there's no way you can do that outside.
Okay, so and then I see that you have audit of the commands.
Right.
So can you stop? Can you do preemption just in the audit part?
Yeah, actually we have some very preliminary support, like what you said. We're trying to collect the history of the command execution and do some prediction, but that cannot ensure the worst case. So the case can always issue maybe just one command to execute for a very long time. So it's we can mitigate that issue, but it's not the 100% solution.
You mean so you can do the preemption in some course granularity, but not in the instruction level, right? Okay.
Okay.